Good afternoon and welcome to this distinguished lecture by Professor Bruce Allen. I know many of you are part of the ongoing meeting, but I will introduce Bruce for the people who are outside this meeting, so please bear with me. Professor Bruce Allen is the director of the Max Planck Institute for Gravitational Physics in Hannover. His career lasting for the last 30, 40 years, he has worked on a variety of topics in gravity and cosmology, including early universe, cosmology, gravitational waves, gravitational wave data analysis, analysis of radio pulsars, gamma ray pulsars, etc. Hard to count. So he was trained first at MIT as an undergraduate, and where he worked with Ray Weiss, who is one of the founders of LIGO and really the person who thought of using laser interferometers to detect gravitational waves, which eventually produced the LIGO and the first detection of gravitational waves in 2015. Later, he moved to Cambridge to work with Stephen Hawking, changing gears, and Bruce would tell the story that Ray Weiss was very upset about this move. But after his PhD and a postdoc stint at a few places, he joined the University of Wisconsin at Milwaukee, where he developed perhaps the first and strongest group working on gravitational data analysis for LIGO. So this was a very influential group that really thought of all the details of the gravitational data analysis for LIGO and developed the first software packages, etc. And in early 2000, he moved to the Max Planck Institute in Germany, where he set up this division of observational cosmology, observational relativity and cosmology. And among many other things that he did, he set up this distributed volunteer computing project called Einstein at Home, which basically uses the spare computing time on our personal devices like laptops and computers as a screensaver that would download the data from LIGO and Virgo and search for gravitational waves from spinning neutron stars. And later, his group also modified to do this to search for radio pulsars and archival radio data, gamma ray pulsars, etc. And they found several new radio pulsars and gamma ray pulsars, but not yet the continuous gravitational waves. But hopefully, that will happen also soon. His work is very well recognized. He's a recipient of several awards and fellowships, which I won't try to list. But also on a personal note, he was quite instrumental in helping getting up the astrophysics effort at ICTS. In fact, the first time he visited ICTS was exactly 10 years ago in October, November 2015 for the inauguration of the Max Planck Partner Group, which we had with Bruce at that time, 2015. It was a funny time, just after the first discovery of gravitational waves, but before the announcement. So a lot of interesting things was happening, and many of us knew that the discovery has happened, but we're not allowed to talk about that. It was a very interesting situation, and I think Bruce gave a public lecture also at IASC saying that gravitational waves will be discovered, etc., etc. And it had happened in the last 10 years, and now we can talk about the actual discovery of gravitational waves. Bruce also was very helpful in even the broader ICTS effort. For example, he played an instrumental role in getting our computing HPC infrastructure get up that in ICTS. He was very hands-on. So he kindly got many of his team members who were maintaining this large computing cluster at Hannover to help us setting up this center here. And he even, I remember him opening this floorboards of our computing room to check the cooling system and so on. So he's certainly very hands-on all these things also. He has a contribution to ICTS outside the gravitational wave effort also. So it's great to welcome Bruce back. So let me ask Rajaram Nityananda to hand over a memento on behalf of ICTS.
Aren't you supposed to give this to me after my talk?
Oh, okay. Let's do this way.
Here. I'll look in this afterwards. Yeah. All right.
Thank you very much, Rajaram. So without any further delay, let me hand over this to Bruce.
Thank you very much. Exactly as Ajit said, my last talk here was indeed 10 years ago. It was about 6 weeks after we'd made the first gravitational wave detection, but it was 3 months before we published that result. So it was strange to be talking about the search for gravitational waves when we'd already found them, but I couldn't say so. The results were published 3 months later. In February, they made newspapers around the world. This is from the Indian Express. You got it right, Einstein. And this observation of the merger of two black holes has become iconic. You can find that waveform on ladies' dresses, on the covers of music albums, and other strange places. My topic today is going to be signals which are not like this. They're not deterministic. They're noise. But they look like noise, and you can only find them by doing coincidence between two instruments. Now, also, as Ajit said, this discovery would not have been possible without Ray Weiss. Ray's the person who, over many years, pushed and promoted LIGO as a project. He worked on many of the technical details. He had a very important influence on me. I met him 49 years ago. He was the first person who taught me how to think like a physicist. Sadly, Ray died about 2 months ago, a few weeks after his 93rd birthday. If you want to learn a bit more about him, I wrote an obituary for Ray, which was published in Nature a few weeks ago. So the topic today is gravitational wave stochastic backgrounds and pulsar timing arrays. I'm interested in stochastic backgrounds of gravitational waves because these give us potentially a way to see what happened very early in the history of the universe. Pulsar timing arrays are a way of observing gravitational waves at nano-Hz frequencies. So to talk about the early universe, I'm going to spend a few minutes on cosmology. One of the cornerstones of cosmology was Hubble's discovery in 1929 that the universe is expanding. If we look around us at galaxies, the more distant they are, the faster they appear to be receding from us. And the relationship between distance and apparent velocity is a linear one. And the slope is the Hubble parameter, 67 kilometers per second per megaparsec. Now we know that this recessional velocity is because the universe is expanding. So really the galaxies are at rest with respect to the cosmological fluid, but the distance on a spatial surface is increasing. And that's the cause of this apparent velocity. Now there's an important quantity here, which is you extrapolate this curve until you reach the speed of light. There's some distance associated with that. That distance, c over h, is called the Hubble length. It's about 4.5 gigaparsecs, 14 billion light years. That's, roughly speaking, the distance to the edge of the observable universe. I'm going to talk during my talk a bit about the Hubble sphere, and you should think of a sphere of that radius around us. But keep in mind that the Hubble constant isn't a constant. It's been decreasing with time, so that sphere was smaller in the past. This is a picture of Hubble, I think in 1922, sitting at the 100-inch telescope. Another important cornerstone of modern cosmology is the microwave background radiation, cosmic background radiation, CBR. This was discovered in 1965 by Penzias and Wilson using this radio telescope at Bell Laboratories in New Jersey. They found that there was a background, 2.7 Kelvin fluctuations that were the same in all directions on the sky. And this was clear evidence that the universe had once been small and hot, because if you run the Hubble expansion backwards in time, that temperature goes up. This was the end of the steady state model of the universe, of then popular cosmological model. And the study of this radiation has taught us a great deal about cosmology. If you subtract that uniform 2.7 Kelvin monopole. You're left with a dipole, a few millikelvin. That's due to the Earth's motion with our local system's motion with respect to the cosmological fluid. You subtract that dipole, and then you see fluctuations on that background. These were first observed with the COBE satellite, then with WMAP. Here's the results from the Planck satellite in a number of different frequency bands at 30 gigahertz and 70 gigahertz. What you see here, by the way, is the plane of the galaxy, which is a contaminating source that has to be removed to study the background behind it. Now, the stochastic background, the electromagnetic one, is an analogy for us. What we'd like to do is to find the gravitational wave analog of this. Before I talk about that, I just wanted to say that this electromagnetic stochastic background is something of personal interest to me in the sense that when I arrived at MIT 49 years ago and started working in Ray's lab, Ray was working on balloon-borne experiments to look at the microwave background radiation. This is Ray working on a bolometer. And this is me at 2:30 in the morning, age 17 or 18, building this is a 10 gigahertz receiver for detecting the electromagnetic stochastic background. So the idea is that there is perhaps a stochastic background of gravitational waves in some ways analogous to this electromagnetic radiation. Now, it's going to have some different properties. For example, as I'll explain, we don't expect it to be thermal. Now, gravitational waves, predicted by Einstein 110 years ago, these share many properties of electromagnetic waves. They travel at the speed of light. They come in two polarizations. But they also have some key differences. So if you want to make electromagnetic waves, you take two charges and you shake them around. If you want to make gravitational waves, you take two masses and shake them around. The key difference is that the electromagnetic radiation is dominantly dipole, whereas the gravitational radiation is dominantly quadrupole. So that's one key difference. Now, if you look across the spectrum of potential gravitational waves, it's very broad. So this is a landscape plot, shows different sources of gravitational waves and different kinds of detectors. And this is indicating frequency going from one cycle in the age of the universe, that's 10 to the minus 18 hertz, right up here past 10 kilohertz. This is a very broad range of frequencies, and in that broad range, there's many possible types of sources. Now, the type that we're talking about here that's labeled Big Bang, well, this upper line here is meant to indicate stochastic background, and it covers potentially the whole frequency range. So at the very lowest frequencies, for example, one might see the effects of that background because it creates correlations in the fluctuations of temperature in the microwave background radiation. That's a very low frequency detector. Later in the talk, I'm going to be talking about radio pulsar timing arrays, PTAs. Those can detect gravitational waves whose periods are tens of years. That's the nano-Hz frequency regime. 1 nano-Hz is one cycle every 32 years. I'll also say some things about gravitational wave backgrounds and terrestrial detectors. So earlier, I alluded to the promise of gravitational waves. The fact that we might be able to use gravitational wave stochastic backgrounds to see the early universe. So let me talk for a little bit about why that is. So as you know, gravity is the weakest of the four fundamental forces, or gravity. But for us, that's a tremendous advantage because it means it's a messenger. This is the Greek god Hermes, the messenger. You can see he has wings on his boots so that he can fly quickly from place to place. So gravitational waves are an ideal messenger because they interact so weakly. The weakness of that interaction means that they can propagate through the universe undisturbed. And they can propagate, if we go backwards in time, at times when the universe was very dense, Nevertheless, it's still transparent to gravitational waves. So that's why we focus on them. Now, by the way, I want to stop and just ask if there's any questions. I'm quite happy to take questions during my talk. I didn't plan something which is going to occupy the entire time. By the way, you should probably start a timer on this for me. I didn't plan something that was going to occupy, so if you want to ask something, please do. Okay. And please feel free to interrupt if I say something that doesn't sound right or that's confusing. So I'm going to show you some plots during this talk. And most of them are going to be variations of this one plot. So I want to describe this in some detail so that we stay connected. So when we're describing radiation, it's very useful to talk about the spectrum of it. How much energy is at this frequency? How much energy is at that frequency? So to do that, it's traditional these days in the gravitational wave community to use a function called capital omega, which is a function of frequency. And here I'll put a GW to remind you that it's gravitational waves, but in a lot of places I won't bother with the GW. So how do we define this? So you just imagine you take some region of space, some volume, and you take some range of frequencies, 100 to 101 hertz, and you count what's the energy density of gravitational waves in that volume, in that frequency range. You take that energy density, d rho gravitational wave, you divide it by the 1 hertz frequency range, and then you normalize it. You normalize it by multiplying it by the frequency and dividing it by a critical closure density. That number, rho c, the closure density of the universe, is just determined by the Hubble parameter today, multiplied by the speed of light squared and divided by Newton's constant. If the universe had more density than that, then it would recollapse. If the universe has less density than that, then it will expand forever. So this is called the critical density for that reason. It corresponds to about 5 hydrogen atoms per cubic meter, roughly. So now, what we're going to do is we're going to plot this dimensionless function of frequency. And I thought, to illustrate what this function means, I would plot it not for gravitational waves, but for that 2.7 Kelvin thermal spectrum of electromagnetic background radiation. So here it is. This is a 2.7 Kelvin black body plotted in this way. For example, it has a peak here that's around 100 gigahertz. That's right, that's short millimeter wavelengths. Another thing you can see from this plot is that it peaks at around 10 to the minus 5. That's because the microwave background radiation is about 10 to the minus 5 of the energy density of the universe. So it's about 10 to the minus 5 of the closure density. That's how to read these plots. Now, we know that this radiation was emitted when the universe was about 1,300 times smaller than it is today. So at a redshift of about 1,300, electrons and protons, which before that time were just traveling around in the kind of thermal bath of the universe, they combined to form neutral atoms. And when that happened, the universe became transparent, and this radiation started traveling to us. Now, it's very unlikely that the gravitational field was ever in thermal equilibrium. It couples too weakly. If it had been in thermal equilibrium, it would have had a temperature, just counting degrees of freedom, that was about 0.9 Kelvin. So roughly speaking, this is the kind of naive expectation. If you were trying to guess what the spectrum might be and you didn't know much, you'd guess, well, maybe a thermal spectrum around the same temperature as the electromagnetic background. Okay, so let me show you some examples now of gravitational wave stochastic backgrounds and just talk about how they're produced. My favorite example is this one. When I was a postdoc in Santa Barbara, I worked on inflationary cosmological models, and I was getting kind of discouraged about them because there were so many of them. And around that time, I think it was 1984, Ray Weiss came through Santa Barbara. We went out for actually for a drive in my car. And Ray said, listen, maybe inflationary models create a stochastic background of gravitational waves that would be visible to LIGO. Could you try and calculate what that is? And so I spent several years actually doing various pieces of the calculation. And that background arises through the following mechanism. Assuming I can untangle this piece of string, I can demonstrate it to you. So the idea is that the modes of the gravitational field are like harmonic oscillators. And when the universe starts inflating, what happens is an observer sees the perturbations, matter fluctuations travel outside of their Hubble sphere. And what you're left with is an almost vacuum field. So the different, oh, you're very kind, thank you. So the different modes of the gravitational field are like harmonic oscillators, and they approach their ground state. What I was hoping to demonstrate to you is what happens in that case. I guess I'm not going to have to do it that way, but this way. So here's the idea. The idea is that initially those oscillators have some frequency, but they're in their ground state. So they're fluctuating with 1/2 h bar omega of energy, and omega, the frequency, because the string is short, is a rather high frequency. Now there's two different things that could happen. If you unroll that string slowly, so that this oscillator could oscillate back and forth many times between the amount of time it takes you to make the string twice as long, it will stay in the ground state. So the frequency goes down, the energy in that ground state remains 1/2 h bar omega, but with smaller omega. But that's not what happens in inflation. What happens in inflation is the frequency drops very rapidly, not adiabatically, exponentially quickly. It's like you roll out the string very fast, and then you end up in an excited state. You see your wave function looks almost like a delta function, but you've made the harmonic oscillator potential very broad. And so you end up in what's called a coherent state. This is called parametric amplification of zero-point fluctuations, or particle creation in an expanding universe. And so you end up with this spectrum that contains a lot of energy. Thank you very much. Okay, I shouldn't have put this in my pocket. So anyway, so the idea was you're in the ground state here, things not vibrating, and then you drop the frequency very quickly. And you remain in the state that was the ground state of that high frequency oscillator, but it's no longer the ground state of this low frequency oscillator. And that results in a spectrum which looks like the following. Now, I actually thought I'd reproduce this. This is the first spectrum I'm aware of that was published for this background. I've just actually reproduced the plot, but I'm going to show it to you in terms of omega. So this is actually energy density as a function of frequency. It's not that dimensionless omega. And here, just as a reminder, is that 2.7 Kelvin thermal spectrum. So let me just talk about this spectrum for a minute. To do that, though, I want to switch to the other units that I was talking about. So here's the dimensionless omega that that corresponds to. So what you have here is energy spread across an enormous range of frequencies. Because if inflation lasted long enough to solve the horizon and flatness problems, it creates fluctuations at a large number of scales. And when these re-enter the Hubble sphere, they create this background of energy. This dip here at the lowest frequencies, these are waves that re-enter the Hubble sphere after the universe becomes matter dominated. So they redshift differently. These are the waves that re-enter before the universe becomes matter dominated. Here, at the highest frequencies, at gigahertz frequencies, this is a cutoff that represents the phase transition. This is a quick phase transition, very simple reheating mechanism at the end of inflation. And a fantastic thing is the amplitude here of this flat part is just determined by the energy density during the inflationary phase divided by the Planck energy density and the redshift at matter radiation equality. This is a beautiful prediction of inflation, and it's one of the holy grails of cosmology, I'd say, is to actually observe this, perhaps with the Big Bang Explorer. Just for the record here, current LIGO limits, also current PTA limits, are many orders of magnitude above this. Here's another example of a mechanism for producing primordial gravitational waves. So here the idea is that you have a phase transition early in the history of the universe. In this phase transition, a local U1 symmetry is spontaneously broken, and you form one-dimensional objects called cosmic strings. This is what it looks like when that network first forms at the phase transition. And then as the universe expands, these strings move under their own tension, and they chop off little loops which start radiating gravitational waves. Other features like cusps on the strings also radiate. And within a few expansions, a few Hubble times, you can cut out a box of Hubble length from the universe, and you see a more or less scale invariant pattern where you have some long strings that pass across the Hubble sphere and then lots of little loops. And this produces a spectrum which looks like the following. So again, I've taken this from an old paper on the topic. But what happens is you have loops that produce gravitational waves during the time that the universe is radiation dominated, and loops that produce gravitational waves during the time that the universe is matter dominated. And those give rise to two different parts of the spectrum. And this spectrum has a characteristic peak at a frequency that's determined by the relationship between these radiation and matter eras. And the plot here is now ruled out by PTA observations. This corresponds to a mass per unit length of the strings, measured in Planck units of around 10 to the minus 6. And current PTA limits now put this flat part here, put this part here significantly lower down. So this is another mechanism for forming gravitational waves early in the history of the universe. Here's a third example. This is, to me, a less exciting possibility. Here, the idea is that in addition to gravitational waves of primordial origin, which is the sort of thing I've been talking about, you can also have gravitational waves which were produced by more recent astrophysical processes. These are things at redshifts of 5 or 10 or 15. And the idea here is that, for example, our gravitational wave detectors pick up signals from inspiraling binaries. But in addition to the ones that we can pick up and say, that was an inspiral, there's also much more distant inspirals that we can't individually detect. And these add together to make a kind of noise, which is also a type of stochastic background. So I would personally call that a foreground, not a background, but this is a question of language. And what you see here is a plot at higher frequencies. This is of relevance to, for example, the LIGO detectors. Showing you, for example, this is the design sensitivity here of advanced LIGO. And these curves are showing over a range of frequencies from, say, 10 hertz to a kilohertz. The contribution of these unresolved binary black holes, that's the green curve, binary neutron stars, that's the red curve, and the sum of these, which is this blue curve. So from my point of view, this would be a very interesting background to detect. But personally, I'd like to see it subtracted, just like that galactic contribution was subtracted from the electromagnetic background, to see the primordial thing that might lie behind it. So this is just a bit of a summary of where we are right now in my talk. We've been talking about this dimensionless energy density and gravitational waves. Here, for example, is that slow roll inflation plot that I showed you before. By the way, there's an old paper by Turner that shows that in slow roll inflation, this has a maximum amplitude of around 10 to the minus 15 at frequencies of interest here. And then I've also plotted a few other things. For example, these are limits from the PTAs, pulsar timing arrays right now. These are limits from the Earth's normal modes. These are indirect limits from Big Bang nucleosynthesis. These are limits that were set by LIGO and Virgo some years ago. This is what we expect from LISA. Sorry, this is what we expect from LISA. Good. Okay. I want to move on now to the next part of my talk, which is, if we could detect such a background, what times in the history of the universe would this be telling us about? So to answer that question, I've got another graph here that I have to explain. So here, this graph goes from early times, 10 to the minus 30 seconds, up to the present time, the universe is about 10 to the 17 seconds old. So this is the time read on their watch by somebody who's just sitting there observing the universe. What do they measure at any given time? So there's two curves here. This one here is the wavelength of a wave picked up today by a gravitational wave detector. So the idea is, suppose we made a gravitational wave detection of the stochastic background. That's in some wavelength region. Let's say it's wavelengths of 3,000 kilometers. So now you could trace that wave back in the history of the universe. And basically that wavelength blue shifts as we go to the back, as we go backwards in time, like 1 over the scale factor. So here's the universe being matter dominated. Here's the universe being radiation dominated. So this is the physical wavelength at any time of that wave that we've detected today. The other curve here is the Hubble length, the size of the observable universe, the cosmological length scale. And that, you see, scales directly proportional to t. So these two curves intersect in the past. That means if we detect a gravitational wave today of primordial origin, primordial and caused by cosmological processes, it was produced on the length scale of the Hubble length. And so it was produced at a particular time in the past. So the crossing of these two curves tells us at what time gravitational waves of cosmological origin seen today at a given wavelength came from. So, for example, LIGO operates at frequencies of 100 hertz. That corresponds to a wavelength of 3,000 kilometers. Trace these curves back, and you'll see they meet at 10 to the minus 22 seconds. I mean, that's the promise of it. You see the universe, what it was like, really at much earlier times than we can with other messengers. This is the corresponding plot for LISA operating at 10 millihertz. So here, the wavelength is 4 orders of magnitude longer. And now you're observing potentially cosmological processes taking place. I'm sorry, I'm pointing to the wrong curve. I should be pointing to this one here. Cosmological process taking place at around 10 to the minus 14 seconds after the Big Bang. That's roughly the time of the electroweak phase transition. Pulsar timing arrays are sensitive at frequencies of order a nano-Hz. That means that the wavelength is tens of light years. And again, if you make the corresponding plot, you can see now that this corresponds to potentially observing processes that took place in the universe when it was about 1 second old. Okay. So this is roughly the halfway point in my talk. I wanted to tell you something about gravitational wave stochastic backgrounds, some mechanisms that can produce them, how they're linked to, particular epoch in the history of the universe. So I'm done with that topic. I now want to talk about pulsar timing arrays, which are a different way of detecting gravitational waves in the sense that, well, they're really not a different way, but let's say they have some interesting differences with the traditional ground-based detectors or space-based detectors that many of you have studied. By the way, just to help me here, let me ask a question. I showed earlier the LIGO discovery paper, the one that was published in February 12th, 2016. Who here has read that paper? Put up your hand if you've read the paper. Okay, all right, good, that's helpful, all right. So a pulsar timing array is sometimes called a galactic-scale gravitational wave detector. So the idea is that you have pulsars. These are rapidly spinning neutron stars that emit a beam of electromagnetic radiation. And that beam, if it happens to sweep by the Earth, is observed as pulses, regular pulses. Now, from my point of view in this talk, I'm not going to treat these pulsars with the dignity that they deserve. Instead, I'm going to treat them as simple clocks. I'm going to assume that pulsar astronomers have successfully subtracted all of the deterministic effects that prevent these things from being perfect clocks. So I want you to imagine that these are actually not pulsars at all, they're just clocks. And so these clocks, as their signals travel from the clock to the Earth, they pass through intervening gravitational waves. And that means that as viewed from the Earth, these clocks tick at different rates. Now this is a popular, so you could think of this as a 6-arm LIGO detector. Each pulsar here being an arm. Now this is a figure taken, I think, from David Champion, and I added a warning triangle here. This is not to scale. Let's talk about what's not to scale here. Well, clearly the Earth is not to scale. But there's something else which isn't to scale, which is, you see, the distance from a pulsar to the Earth is typically thousands of years. That's thousands of light years. Whereas the gravitational waves that we're sensitive to, which is supposed to be this kind of background wiggle in the green plot, those have wavelengths of, say, 10 years. So one thing that's wrong with the scale here is that the length scale of these wiggles on the green background should be 10 years. Shouldn't be so long. And by the way, in this picture, the pulses coming from this pulsar, they might be a few milliseconds from pulse to pulse. So that's about 10 to the minus 10 years. So along one of these yellow paths, followed by the pulses, there's a train of something like 10 to the 13 pulses traveling down that. And sources here of interest, these would be at least hundreds of megayears away, so they wouldn't be anywhere on this slide. They'd be a few kilometers away from us on this scale. So if you want to understand how a pulsar timing array works, there's a very nice way to do it. So what I've done is I've replaced my pulsars with lasers. Those are clocks. And the effect of a gravitational wave on the propagation of light was first calculated by Sachs and Wolf in the 1960s. They were interested in understanding how the temperature of the microwave background would be affected by intervening gravitational waves. And it turns out their formula, because of the principle of equivalence, also describes, for example, how the frequency of this laser, this clock, would change. And the way that the frequency of the laser changes, its fractional change, it's exactly the same as the fractional change in the spin rate of the pulsar as seen from Earth. So what Sachs and Wolf said is the following. They said, suppose you make a space-time diagram. So this is a space-time diagram where the Earth is fixed here. That's a fixed point in space. Time's going up. Here's a pulsar that's located at some distance L away from the Earth in direction p hat. And the Sachs and Wolf formula tells us how much time delay gets added to a light travel path from the pulsar to the Earth because of the gravitational wave. And it says if you want to know what the time delay is due to the gravitational wave, you integrate along this null geodesic. I've labeled this with the parameter s that goes from 0 to L. You integrate the metric perturbation hij dotted into the direction vector to the pulsar along that path. So this is a point p minus L plus s here, and L minus s p hat. That just traces out a point along this dotted path. S equals 0 is there, and S equals L is there. So if you take this formula for the time delay, you can differentiate that to find out the redshift. Now, redshift is a strange word to imply here, to use here. It would make sense if we were looking at lasers which are red. They might turn a little bit bluer or a little bit redder because of the passage of the gravitational wave. But here we can use that word anyway to just describe how the pulsar clock frequency changes, whether the frequency goes up or down. It's the same thing. So anyway, if you differentiate this once with respect to time, you get a redshift, a fractional change in frequency. And if you think about this integral, if you take the derivative inside the integral, you end up with two boundary terms. For a gravitational wave traveling in the direction omega hat, you can do this integral and you end up with the two boundary terms, just give you back h. One of these is the gravitational wave strain evaluated at the Earth here at the time that the pulse arrives at the Earth. The other term is the gravitational wave strain evaluated at the location of the pulsar at the time the pulse left the pulsar. So the change in the frequency of this clock depends upon the gravitational wave amplitude here at the time that the pulse left the pulsar, and at the gravitational wave strain at the Earth, time the pulse arrived here. And so the way that a pulsar timing array works is it exploits the fact that this Earth term is the same for all different pulsars, apart from this antenna pattern function. Whereas the pulsar term here, being evaluated thousands of years distant and at different times, is uncorrelated between different pulsars. Yeah, where does this term come from? It comes because if you have a plane propagating wave, it has a phase relationship. There's an e to the 2 pi I t minus omega hat dot x for a wave traveling in the omega hat direction. And if you substitute that into this formula here, you see there's S dependence both here and here. You end up with that factor. And we've worked this out very carefully. There's an article that Joe Romano and I published in Classical and Quantum Gravity a couple of years ago where we worked this through step by step. It's a nice exercise. It's not hard to do. Okay. So here's a nice way of thinking about it, if you like. As I said, the path by which the pulses come from the pulsar to the Earth, that train track has something like 10 to the 13 pulses along it. The pulses are 10 to the minus 10 years apart, and the path is 1,000 years long. So what happens is, when the pulsar is sending these pulses down the track at the pulsar end, the metric strain at the pulsar at the time that the pulse leaves modifies the ruler length that you use to set the distance between these cars. And then, when the pulses arrive at the Earth, the ruler that you use to measure the separation also depends upon the metric perturbation at the Earth. So that's the reason why these two different terms appear. One is from setting the distance between the cars when they leave, and the other is from measuring the distance between the cars when they arrive. So the long-term goal of pulsar timing arrays would be to make a sky map something like this. Now, they're not doing this now. I hope that they will do this in the future, but this is the long-term goal. So the long-term goal would be to say, here's what the gravitational wave sky looks like in this frequency band. We can identify some discrete point sources of gravitational waves. This is a supermassive black hole binary, two black holes of mass 10 to the 10 solar masses, orbital inclination of 43 degrees, orbital period of 76 years at a redshift of 0.67. Here's another one, somewhat different parameters. And then, in addition to these resolved individual point sources, there's some background pattern here, perhaps characterized by multipole moments, a bit like the stochastic background. So that's the long-term goal. Now, unfortunately, PTAs are not at that point yet. So, yeah. No pulsars here? So, you know, if you have a LIGO detector with two arms, that's sensitive. The response function looks like a peanut, you know, perpendicular. So you're sensitive to things from above and below. You're not sensitive to certain directions along the arms and in between. But the response is very broad. The same thing is true for the pulsars, right? The pulsars represent different arms. And actually, because there's many of them, not just a couple of arms, you're actually sensitive to all directions. So does that help? So don't mix up my gravitational wave sources here with the pulsars, which we're using as detectors. Right? The pulsars have specific sky look. No. Good. I'm glad you asked me the question. Thank you. Okay, so the idea here, so the goal of pulsar timing arrays is to try and measure this gravitational wave stochastic background. And like the electromagnetic background, this should have some distribution on the sky. You know, some particular radiation coming from one direction, more or less coming from another. And so the idea is this is kind of supposed to be an analogy with the microwave background radiation. Remember the pictures I showed you from Planck, for example, you could see the plane of a galaxy. That was some strong sources. So here the idea is that we're not going to see sources from our galaxy. Those aren't low enough frequency. But we will see, for example, some point sources maybe from far away. Okay. Are there other questions? I'd really be happy if there were. I don't like the sound of my own voice that much. Okay. Okay, let me go on. Well, they would if you had some other way of identifying them. But it's quite possible that these would be detected with, oh, the question was, would these serve as standard candles? I guess they would if there was another way of detecting them. If they could be seen optically or in some other way, yes. But I suspect that if PTAs get to this stage, probably they will be the detectors at that point, because these are going to be at relatively large redshift. Yes?
How do you mitigate the effects of intervening medium?
Remember my picture with Hermes the messenger and gravity being a very weak force? That's the beauty of the gravitational waves. They're unaffected. They're the intervening stuff.
I'm talking about the gravitational redshift that would occur probably because of some astrophysical object in between Earth and the pulsar.
Yeah, so as I said earlier, I was treating the pulsars as if they were perfect clocks. Now, there are many effects that disturb pulsar rotation as seen from the Earth. For example, there's interstellar weather. If a cloud of ionized material passes along the line of sight, that causes dispersion and so on. For the purpose of my talk, I'm going to assume that those things can be removed, or at least modeled.
What is the violet background? Violet background is colors.
Oh, I see. Oh, the color scheme was just meant to be an analogy with the microwave background radiation. Namely that we see radiation in addition to, so this is again, the long-term goal of PTAs. The idea is that in addition to saying, okay, there's gravitational waves coming from discrete point sources, there's also some diffuse background coming from all directions. And so this was just meant to show the relative amplitudes, that there's more radiation coming from one and less from another. A bit schematic.
Thank you. Thank you for a nice talk. I just want to know, like in your theoretical calculation of the gravitational wave background, have you already taken into account the lensing effect by
Which effect?
Lensing effect by intervening objects?
No, I'm not taking, again, you know, the effects of lensing will, just like on the microwave background radiation, lensing has, you know, does have some effect on the small scale structure there. It will also have some effect on the structure here. I'm really talking about zero order things right now. I'm happy if there's other questions. This is a good time. Yeah. Oh, I can't answer that question. It's a good question. I don't know. I only wanted to just try and say this is the long-term goal. Okay? We're very far away from that now. And I'm going to talk a little bit more about reality, where we are now, in the next few slides. Okay, let me go on, but please interrupt. Thank you for asking the questions. So let me just say a little bit about how pulsar timing arrays go about this detection. So as I said, the idea is to correlate the signals coming from different detectors, different pulsars. So if the gravitational wave background were strong enough, this Sachs-Wolf effect would mean that we could actually see the gravitational waves just in the timing residuals from a single pulsar, the deviations of that clock from regular ticking. And indeed, in the 1980s and 1990s, some upper limits were set on the gravitational wave stochastic background at nano-Hz frequencies, exactly in that way, by saying that, well, the fluctuations that we see in the arrival times are not too big, and therefore we can set an upper limit on the gravitational wave background. But we know now that the gravitational wave background is too weak to use that for detection. And so you have to correlate the arrival times to many of these pulsars. And to do that, there's a very critical thing called the Hellings and Downs curve that enters in. So the idea here is that the pulses traveling from pulsars are traveling through the same gravitational wave background. And so they get correlated because of that. the Earth term is the same for all the pulsars. The pulsar terms are different. And because the Earth term is the same, you get a pattern of correlation which depends upon the angle in degrees between the line of sight to the pulsars. So this curve, for example, is a prediction that if I look at two pulsars that are almost exactly in the same direction on the sky, then the gravitational wave-induced fluctuations in the arrival times will be 0.5. That's because the pulsar terms are uncorrelated with each other, but the Earth terms are correlated. And if I look at two pulsars that are at 90 degrees apart on the sky, on the average, they'll actually be anti-correlated. And if I go back to 180 degrees separation, they'll be correlated again. By the way, pulsar timing arrays are long-arm gravitational wave detectors, not like LIGO, for example, which is short-arm. And that's the reason why this is not just a purely quadrupolar pattern, a second Legendre polynomial where this value would be the same as that value, in case you're wondering. So recognizing this pattern in the data is considered the smoking gun of gravitational wave detection. It's like recognizing this chirp signal was the sign that we had detected gravitational waves. I did want to say very briefly where this curve comes about because it's important. This is the way it comes about is exactly from that factor that you asked me about earlier. In the antenna pattern response, there's this 1 plus omega hat dot p in the denominator. So this is the response of a pulsar to a gravitational wave traveling in direction omega hat, which is plus polarized. It depends upon the direction to the pulsar p and on the polarization tensor of the gravitational wave traveling in direction omega. And if you take two different pulsars, pulsar 1 and pulsar 2, so they have two different direction vectors, p1 and p2, this is the correlation between the Earth terms when summed over the two different polarizations. And if you average this correlation over all the directions of gravitational waves, you end up with this quantity here, this mean correlation, the Hellings and Downs curve. So it's important for the rest of my talk just to stress that this correlation here that we expect is the mean value. It's the average that you would expect. It's not necessarily the correlation that you would observe for any particular set of pulsars in any particular gravitational wave background. The importance of this curve, of recognizing this curve for pulsar timing arrays, is made rather clearly in this document. It's the International Pulsar Timing Array Checklist for the Detection of Gravitational Waves. And it says, to demonstrate that gravitational waves are creating some of the noise in pulsar timing data sets, observations must exhibit the Hellings and Downs curve, the angular correlation function associated with gravitational waves, as well as showing that there are no other reasonable explanations. So I want to discuss right now the state of that particular question. This is the current results from 5 different pulsar timing arrays. The Parkes pulsar timing array, mostly based in Australia, published a paper in the middle of 2023. They observed 24 pulsars for 18 years, and they say there's no support for or against seeing this pattern of correlation. The European pulsar timing array, together with the Indian pulsar timing array, published in 2023 their study of 42 pulsars observed over 25 years. If they use the full 25-year data set, they say that there's marginal evidence for seeing that Hellings and Downs pattern. If they use only the last 10 years of the data, then they say there's evidence. Chinese pulsar timing array, they observed 57 pulsars for 3 years. They say there is some evidence for seeing that pattern. Nanograv, the North American nano-Hz Observatory, they've observed 67 pulsars over 15 years, and they say there is compelling evidence for that curve. This compelling evidence is not at the 5 sigma level. It's somewhere between 3.6 and 4.2 sigma. And then most recently, MIRTIME, using 83 pulsars observed at MeerKAT for 4.5 years, has a very curious conclusion. Under different assumptions about noise processes, we can produce either what appear to be compelling Hellings and Downs correlations of high significance, 3 to 3.4 sigma, with a spectrum close to that which is predicted from the merger of distant supermassive black hole binaries, or surprisingly, under slightly different assumptions, correlations that are insignificant. So yes.
Just a quick question. What actually helps you detect the gravitational, the stochastic background better? Is it greater number of pulsars or is it a longer period of time?
Both. Both. So your sensitivity increases as you add more pulsars to your array and as you get more data. And the more data helps a lot because very likely the spectrum is a low frequency dominated spectrum. So as you take more data, the amplitude at low frequencies rises rapidly. That's the hope.
Right. I was just trying to maybe rationalize, the fact that nanograv has compelling evidence. I noticed that it has 67 pulsars, but fewer number of years, whereas say the Parkes pulsar timing array has more number of years, but fewer pulsars. So is it fair to say that the greater number of pulsars helps you more than number of years? Is that fair?
It does, although I think it's also fair to say that there ought to be stronger evidence in some of the others. So this isn't entirely, let's say to me, a completely consistent and satisfying picture. Okay, yeah.
In the second one, what is the meaning of marginal evidence versus?
Oh, yeah, again, they had 25 years of data.
Yeah.
And if they analyze that 25 years of data, they see marginal evidence. Now, then they took just the last 10 years of data. And there, if they say they just take the most recent 10 years, they say evidence. That's kind of backwards. It should be that the longer data set gives you higher signal to noise ratio and greater evidence. So this is odd. Yes, you should be puzzled by that. No, the 25 years includes the last 10 years of data also. It's the full 25 years or just the last 10 years of it. I know, yes, your reaction is the right one. Go ahead.
Can I ask a question? So where does the information about the source of these stochastic backgrounds, say for example, cosmic strings or astrophysical background?
You'll see right now that we're at a much earlier stage than that. We're just at the stage, for example, before even Penzias and Wilson made their observation of the 2.7 Kelvin sort of black body. We're still trying to even measure the monopole. Okay?
But ideally, should they turn up in the Hellings-Downs curve?
No, this Hellings-Downs curve is quite universal. It doesn't really depend upon what the source of gravitational waves is. In the calculation that I did, we did an average over directions of the incoming gravitational waves, but you could perfectly well take one point source of gravitational waves and instead average over many different pulsars. Let me come back to your question because I'm going to say something about that. What comes? Are you standing up because I'm running out of time or just to pass around the microphone? All right, no, it's okay. I'm watching.
Excuse me.
Yeah.
Excuse me. Yeah, I'm sorry
Wave
for
your hand.
interrupting.
I can't see who's talking.
No, I'm online. I'm talking online.
Okay, good.
So yeah, so you in the meantime they're talking about different assumptions either leading to Hellings-Downs or insignificant results. So what are these assumptions they're talking about? Slightly
Yeah,
different.
these assumptions are about the noise and the pulsars. You see, in explaining how PTA worked, I said I'm going to assume that the pulsars are perfect clocks. Unfortunately, they're not perfect clocks. In fact, when the individual pulses arrive at a radio telescope, in fact, they look quite different from one another. It's only after you average many of them together that you even see a consistent pulse profile. And so, in fact, there are uncertainties in measuring the arrival times of those clocks, and the assumptions about those noise processes strongly influence their results.
So it's basically different methods being used to like process those noises leading to different results.
Yes.
Okay.
Yes.
Yeah.
And by the way, there's a nice paper written by Rutger van Hasteren where he argues that that the correct assumption to make about the noise processes is the one, unfortunately, which leads to the insignificant rather than the significant correlations.
Oh, okay.
I'm agnostic on that question. But so let me just continue. So I want to talk now. These are the reconstructions of this Hellings-Downs correlation curve as produced by these 5 different collaborations: the Parkes pulsar timing array, European pulsar timing array, Chinese pulsar timing array, nanograv, and MIRTIME. So again, here what you see, for example, is the angle between the lines of sight to the two different pulsars. And then this is their estimate of the pattern of correlation that they see. So let me just talk about one of these plots. Try and explain what's going on here. So here's the nanograph plot. Nanograph observed 67 different pulsars. So that means that the number of different pairs of pulsars, it's n times n minus 1 over 2. In this case, 2,211 pulsar pairs. So what they did is they took their 2,211 different pulsar pairs and they binned them. So for example, this point there represents all the pulsar pairs whose angles were in between about 0 degrees and say about 20 degrees. So in that point there's about 147 different pulsar pairs because they've divided the pulsar pairs evenly among these 15 angular bins. And what this point represents is it represents the average correlation that they observed among those 147 pulsar pairs. And this bar here represents the uncertainty in estimating what that mean correlation was. And now they've repeated this for these 15 different angular bins. And this is the pattern which they got. So this looks very encouraging. You can see that, for example, that these error bars here, or uncertainty bars here, there's a few points that don't cross the Hellings and Downs curve like this one, but many of the points do. So that looks very good. But then it leads us to the following question. This is a research question that I've been working on a bit for the last few years, which is how big do we expect those uncertainties to be? Could we say that this is or is not consistent with the Hellings and Downs curve? Is this what we should expect or not? Yeah.
Say that there is no signal. Like, for example, if there is a Hellings-Down curve here,
Yes.
Meaning, so there is, I mean, here you can see something like a pattern.
Yes.
You could also draw a line which would never cross 0, I think.
Yes.
I mean,
Very good question. Yes, that's exactly the question that I've been working on. So it's the right question to ask. So yeah, please.
Is that a fit or is that a fit or?
Oh, yes. So this dashed curve here is exactly this this calculated Hellings and Downs curve. It's the thing, it's this formula. So it's the thing that we're trying to see if it's in the data. Okay. That's right. It's no parameters. So this question really comes down to a question of what's the variance around these points. If we make these measurements, for example, in universes drawn from some different ensemble, how often will we land, for example, a certain distance away from this curve? And that question was actually addressed in 2017 by Ruber and Holder in this paper. They considered a very special case, which I would call pure cosmic variance. They assumed that there was infinitely many pulsars spread uniformly on the sky. They assumed that the pulsars were completely free of any measurement noise. They assumed that the sources were a Gaussian ensemble. That is to say, there was many weak sources which added together to give you a Gaussian-like statistic. They assumed that all the sources were radiating at exactly the same frequency, which was commensurate with the observation time. And then they used CMB techniques, sky mapping techniques, to compute the variance of that. And I've been working on this quite a bit over the last several years with my collaborator, Joe Romano, and we published a paper at the beginning of this year in which we've managed to drop all of these assumptions. So for example, the correlation pattern that you get doesn't just depend on the the fact that one realization of the universe or another realization might be different because the amplitudes and phases of the sources might be different. It also depends on the noise in the pulsars themselves. So we've dropped the assumption that the pulsars are free of noise. They assumed that there was infinitely many pulsars. We actually did a calculation where we can put a specific set of pulsars at specific sky locations. And finally, we also dropped the assumption that all of the sources are radiating at exactly one frequency. We actually said that the sources can have an arbitrary power spectrum. And I just wanted to show sort of what the result looks like. So what we find is we compute the variance away from the mean. How far do we expect in an observation the Hellings and Downs reconstructed curve to come? How far we expect it to come away from that curve? And it turns out to be the ratio of two things. One quantity is a geometrical quantity, which only depends upon where the pulsars are located on the sky. And the other quantity here is an effective number of frequency bins in which the gravitational wave signal dominates the noise. This number of frequencies might not be an integer, and it might be very small or it could be large. So what do these two quantities look like? The numerator here is a geometric quantity that only depends upon where the pulsars are located on the sky. If you have an infinite number of pulsars, you actually get a curve that looks like this. It doesn't quite touch zero at these two places. In the pluses here, I've drawn, for example, what you would get if you used the 67 nanograph pulsars in the 15 different angular bins that you picked. So there's 15 of these points at locations that correspond to the angular bins that Nanograv used in their reconstruction. And you can see that using discrete pulsars rather than an infinite number of them has, roughly speaking, doubled the variance away from what it would be if you had a large number. And so if the number of frequency bins was just one, then what happens is that you end up with this envelope here, this dotted curve around Hellings and Downs. That's in the case of an infinite number of pulsars. Or by the scatter, these plus symbols here around the Hellings and Downs curve in the case where the number of frequency bins is one and you just have the 67 pulsars. So we now have a way to actually calculate the variance. Yeah.
But I'm trying to figure out, so when you are getting the cosmic variance, see for CMB, what we do is that these are anisotropic map, and you say one specific map which is anisotropic. Are you taking an anisotropic map here as that realization?
So since you know this topic very well, I'll just say what the answer is. So what Rober and Holder computed as the variance, it's exactly the square of the mean divided by 2L plus 1. So they did a harmonic decomposition, and that was the variance. Okay. A very technical question with a very technical answer. Okay. So I think I want to stop here, but I'm happy to keep answering questions. I just want to say that the gravitational wave stochastic background offers us potentially a picture of the very early universe. We don't have that now. I expect we're probably not going to have that in my lifetime, but I think it is something that will be achieved. Recent pulsar timing array data shows evidence for a nano-Hz stochastic background. It's consistent with the Hellings and Downs pattern. I think it's still fair to say that we don't know yet if that match is as good as would be expected or not as good. There are many gravitational wave models. We've heard about some of these actually in the past days that fit this PTA data. But at the moment, there's not enough signal to noise in that observation to even confidently say it's a detection. So we really can't constrain the sources very clearly, other than say placing some upper bounds and saying that it's got to be, it can't be too loud. The work I was just talking about gives us some clear expectations of what pulsar timing array detections will look like. And I hope I'll be back here in 10 years talking about a confident detection of this kind. Now, normally I would end my slide here and you could applaud, but I thought it would be fun to put up also one other slide from my last visit here. So this is again from the 6th of November, 2015. And this was the LIGO India schedule at the time. And I'll point here to the bottom here. Now, I think that the point that Jan Harms made earlier today is very true. I mean, gravitational wave detection is not a short timescale thing. It's something that you do over decades. So with this as the starting point, I'm personally really delighted that the government of India's e-marketplace purchase and price portal has actually got the bidding right now for the engineering, procurement, and construction of infrastructure and vacuum equipment for establishing LIGO India. I gather the closing date has now been advanced a few more days. It's, I guess, next week now, for approximately 160 million euros. So LIGO India is going to happen on a rather short time scale. I'm very excited about that. Thank you.
Thank you, Bruce, for this exciting summary and perspective.
Actually, I have first question. Sorry. I'll give mic to everyone. The only question. So when we'll observe, when we'll have significant detection and when we'll observe, in the omega F curve, are we going to get one point or one patch? Because that will depend on how far the pulsars are. We have to bin them in distances. Is that the idea?
Yeah, so the way to think about this is that pulsar timing arrays are low frequency detectors because they look for fluctuations in the arrival times of the pulses, but not for fluctuations on short time scales, but for fluctuations over years that are correlated. So these are caused by gravitational waves, which also have periods of years. So in those plots of omega of F that I made, a year is about 10 to the minus 8 hertz. 10 years is around 10 to the minus 9 hertz. So what PTAs are doing is they're trying to observe a piece of that curve at frequencies around 10 to the minus 9 hertz.
And the longer you go, more lower you
Yes,
keep observing.
Exactly. So a civilization that could do these observations for 1,000 years could go down to frequencies of 10 to the minus 11 hertz.
Nice, thanks.
And if we could find somewhere in the universe some really precision clocks that were very precise on short time scales, then we could use these as detectors also and go at other frequency scales.
Nice. Very nice. Thanks.
Thank you.
Hello. So I have a small question. In the initially thing, you have said that based on the frequency band that we choose, and if we wait for a long time back, for the current observatory.
We go back to the one of the plots here. I think you're asking about
the previous one.
this,
Year or the other one. So
this one or not?
This or the previous one, where it is 10 to the power minus 20.
Let's pick that one as a starting point. Good.
So this is the current scenario that we are having speed of light.
Let me talk through this because you're right to ask about this. This is confusing. Okay.
Okay.
So let me just say. So here's the idea. Suppose that we observe gravitational waves today that have a wavelength of 3,000 kilometers, and they were of primordial origin. What does that mean? It means we can go back in time. We can watch this wave of primordial origin. As we go back in time, the wavelength is going to get shorter and shorter and shorter. That's this plot. So when we get back to 1 second in time, that wavelength is around a centimeter, for example. As we keep going to earlier times, that wave is getting shorter and shorter and shorter. Now, here's the neat thing. At some point in the past, the Hubble length, that Hubble horizon, is going to pass that. It's going to equal it. And so if the gravitational waves were produced by a cosmological process, cosmological processes happen at the Hubble scale because they're cosmological. That's kind of what it means. Then that was the time at which the production took place. So the idea is that if you take these two assumptions, that we observe something that's of primordial origin, if you assume that we observe something and that it's of primordial origin, cosmological origin, then this argument works. Does that make sense, or?
Okay, that's clear.
Okay. I'm sorry, can you use the microphone? Absolutely, we can. We can, because you see, what's the cosmological process for inflation? So we have we have these vacuum fluctuations, okay? So you imagine the pendulum's at rest, and then, very suddenly the frequency drops, okay? And you generate, but that dropping in frequency, the amplification, that occurs when the modes re-enter the Hubble sphere. So if you look at any given frequency mode, as the universe evolves in inflation, that gets redshifted. It stretches until the wavelength is much longer than the Hubble length. So it moves outside the Hubble horizon. When it moves back into the Hubble horizon, that's when you start to see it oscillate. And so this crossing, so what happens is that for the stochastic background, from inflation, this crossing occurs at all wavelengths, just at different times. So that's why you could look back with the detector at a longer wavelength, and you would see the universe at a different time, but there would be also inflationary perturbations re-entering the Hubble sphere at that time. That's why you get such a broad, flat spectrum.
Okay. My question was contrasting resolvable sources versus the stochastic background. It just seems to me that it's easier to measure the stochastic background with PTA as opposed to resolvable sources, and which is completely the opposite with it, or it appears to be the opposite with LIGO, where you see resolvable sources, but we've yet to see a stochastic background. Is there an easy way to understand that?
So first of all, let's suppose that the PTA observations are real. It's not possible from the measurement that they've made to distinguish between whether that's a single point source or a uniform isotropic background. You would not see something different in those two cases, not with the level of sensitivity they have. Now, if you imagine that you have a very sensitive instrument, then the PTA can have quite a lot of directional resolution because each different pulsar represents a different arm. And by correlating the different ones, you can get something directional. By the way, just a comment, if we knew the distance to all of the pulsars precisely means within one gravitational wavelength, let's say to within a couple of parsecs, then your pulsar timing array would become a phased array. Then you'd know what the difference between the phases at the departure and arrival times are. And then the antenna pattern would look like a bunch of very narrow fingers. As many fingers as you had gravitational wavelengths between you and the pulsar. And each different pulsar would have its own antenna pattern with its own fingers. And then by using them all together, you'd have an incredibly directional receiver. So in fact, there is now, I think, at least one pulsar where the distance is known quite precisely. For me, one of the wonderful things would be if clever radio astronomers figure out how to determine the distance to pulsars precisely, because then pulsar timing arrays would become phased arrays with incredible pointing precision.
So just to get a quick clarification about your first answer, what you're saying is with the current measurement, we cannot be sure whether it's actually a stochastic background or a single resolvable source?
We can't even be sure whether it's a gravitational wave background at all, or just noise, in my opinion.
Because the lore right now is that it's a stochastic background of merging supermassive black holes, but what you're saying is not to read too much into that.
I personally think that, that the evidence right now doesn't let you decide between the possibilities. I don't know the actual theorem, but I'm told that in information theory, you can convert a signal to noise into the number of bits, different options that you can decide between. And right now, the number of bits of information in this observation is sufficiently low that I think you can't really distinguish between the possibilities.
Hi, Bruce. Thanks for the talk. I had a quick question about, for the different PTA measurements, different PTA surveys that have made the measurements, there are certain pulsars that are common between those PTAs. Do these surveys agree on the noise systematics of at least the common pulsars?
So if you look at these different pulsar timing arrays, I think in all they have about 120 or 125 different pulsars. Whereas, of course, if you add up the number of each one here, you get a number that's significantly larger. So as you say, these PTAs have pulsars in common. Now, the international pulsar, and all of these PTAs, by the way, have made their data public. The different PTAs are now trying to produce a merged data set And I think part of that is trying to come up with common noise models for the different pulsars that each one has observed independently. So I think what you're asking for is in progress, but I'm not a member of any of these collaborations, and so I just watch this from the outside.
So one of my questions was actually going to be about the phased array. So thanks for mentioning that. The other question I had was about the Hellingsdowns measurement. I think you pointed out on the slide that, of course, it's going to be highly correlated because the same pulsars contribute to different bins there. So what Sanjit was asking about, whether you can draw like a line and you know, that might already be excluded, except that, you know, just because we're plotting it in like this, not plotting the correlations, it seems to the eye that that's not excluded. Is that really true?
You know, this is a difficult thing to say. Ultimately, the way that the question is really this: the question is, could random noise, as opposed to a gravitational wave background, have given rise to this same pattern? How likely is that? And the assessment of that is made using a so-called optimal statistic. It turns out that the statistic that PTAs have been using to do this assessment is actually not optimal. There's a paper on the arXiv by myself, Joe Romano, and Rutger van Hasteren from about 2 months ago about this. But there are techniques, and so when we say, you know, when they say 3.6 to 4.2 sigma, they're trying to assess the false alarm probability, that p-value, by asking how likely is it that random noise would give this particular pattern. I think that's the best answer I can give to your question.
Can you quickly say what causes the loss in optimality?
Oh, yes. If you're analyzing LIGO data and you assume you've got a template in Gaussian noise, then the Neiman-Pearson lemma tells you that the optimal statistic to use is to compare two different likelihoods, take the ratio of two likelihoods. One of those likelihoods corresponds to a Gaussian centered at 0. The other likelihood corresponds to a Gaussian centered at your template. And it turns out that that is exactly the same statistic you get as if you wrote down a signal to noise ratio and you maximized it. So maximizing the signal to noise ratio is equivalent to the Neiman-Pearson test for a signal in linear additive Gaussian noise. But that's not what PTAs need to do. PTAs are instead comparing a signal hypothesis where you have the Hellings and Downs pattern of correlation to a null hypothesis where there is no correlations. This corresponds to asking, not comparing two Gaussians that have the same variance in different means, but rather to asking, do we have Gaussian A, 0 mean and this covariance matrix, or Gaussian B, 0 mean and a different covariance matrix? For that case, it turns out that maximizing the signal to noise ratio, which is what they've traditionally done for the optimal statistic, is not the Neiman-Pearson statistic. The Neiman-Pearson statistic is slightly different. And so what we did is we first derived the Neiman-Pearson statistic, and then we actually modified it to make it robust against the pulsar noise modeling, this thing that Meerkat was having trouble with, saying that their results depended upon the pulsar noise modeling. So effectively, what we did is we derived the Neiman-Pearson statistic rather than a signal to noise ratio. And then we showed how to modify that slightly to make it more robust.
Okay, thank you.
Welcome.
So I had, like, if we had a rather more optimistic scenario in the sense of multi-messenger, not the multi-messenger we talk of in BNS mergers, but they targeted pulsars, and we had CW observations from them, and they form part of this pulsar that nanograv observes as well. Would that help in any way? Like, it's mostly a follow-up to your answer to Sarsh's question on how to get directional antennas, and if you could get some distance measurement. And this is likely not to be the scenario, but if this was to be the scenario.
So it's absolutely the case. So if you look, so if you knew the distance to pulsars, then the antenna pattern of a single pulsar would look kind of like a flower with petals. And the petals would be longest for the signals coming from behind the pulsar. and they'd be the shortest for the signals coming from the opposite direction from behind you. So a pulsar in the sky is, roughly speaking, most sensitive to sources nearby and least sensitive to sources on the opposite side of the sky. Now, because we don't know the distance to pulsars, instead of having this many petaled flower, instead you just kind of get an average curve like that. So that means that pulsars are sensitive to, more sensitive to sources in one direction in the sky than to the other. So that means that ultimately when there's enough signal to noise in the measurements, you'll be able to say something about where the sources are in the sky. But you can't do that at low signal to noise. Now, in terms of multi-messenger, what was the other observation that you were thinking of combining with?
I was just saying, like, if there was a way to estimate the distance in terms of multi-messenger observation.
Distance to pulsars.
The targeted searches for CWs, say, continuous waves. And if a few of these pulsars were to.
Oh, absolutely. If continuous gravitational wave searches succeed, you may well be able to use that information to infer something about the distance to pulsars. I'm actually not sure how that would work, because it's kind of degenerate with how big the mountain on the pulsar is, right? You make the mountain on the pulsar.
Yes, but if there are some spin down models that then.
But maybe clever people can use that information. I would love to see continuous gravitational wave detections from pulsars. That alone would be worthwhile. The way that people determine the distance to pulsars is by observing scintillation patterns. And how that works exactly is something I don't understand well. There's probably other people here who do understand how that works. You could ask about.
Since I have the microphone, I'll ask a question. Hi, Ruth,
sure.
I'm here.
Okay.
Hi. Since we're on that slide, I wanted to understand better where the error bars are coming from. The way I understood you, it was just that there are multiple pulsars and we, average them and the spread is somehow represented. But then shouldn't the timing residuals themselves have an error, because we need to subtract all sorts of terms, which is that folded in, and how?
They do. So the idea is that this point here represents an average of the correlation between 147 different pairs of pulsars. So I could give you a set of numbers. I could take a Gaussian process, a Gaussian with mean 1 and variance 1/2. Now I could feed you 10 numbers from that, and I could say, Frank, please estimate what the mean of that Gaussian is. And you'd estimate it, but you'd also have an uncertainty. You'd say, well, I've estimated that the mean is this, but based on what I've been able to conclude about the variance between these measurements, I think there's some error or some uncertainty. So what these bars represent here and here is the uncertainty in estimating that mean. There's 147 different measurements, but they're contaminated by noise, and so you can't estimate the mean exactly.
But I guess I'm asking is, if you throw me 10 numbers and all of them are biased by 0.1, then no matter how good I am, I'll be off. Isn't there a risk that the timing residuals are affected by some systematics?
Yes, that's absolutely possible. For example, it might be that all of the observatory clocks, for example, have an error in them, which happens to just be the same at all the observatories. So that would give you a correlated signal between pulsars. And the pattern of that signal, though, wouldn't depend upon the angle between the pulsars. It would just be an overall constant. So in fact, in doing these kinds of studies, the PTAs do also try and see if there's signs of other patterns in their data. For example, if they see a constant pattern that says, aha, there's something wrong with our observatory clocks. There's a common error that's creeping in, for example. Does that help?
Yep, thanks.
Okay.
Question is that
okay, it's on now.
I mean, it's a kind of related question. Suppose we have only 3 pulsars, 2 on the antipodal points and 1 on the plane perpendicular to it, with some infinite precision in measurements. We would still be able to probe this curve, right?
You'd be so if you have those 3 pulsars,
yeah.
Let's see, the way that you set them up, 2 of them are separated by 180 degrees, and 2 of them are separated by, 1 pair is separated by 180, and 2 pairs are separated by 90.
Yeah.
Is that right?
Yeah.
Yeah. So that would let you estimate exactly 3 points, right? 1 point here from 1 pair at 180, and 1 point here at 90 from 2 pulsars. That's the idea. That's what's going on here. Yes, and the point is, you see, there's these blue bars here actually represent 2,211 different sets of correlations. That's been sort of reduced here and presented. I'm happy. I mean, by the way, people who are bored or who have other things to do are welcome to leave. I won't take it personally, but I love talking about this, so I will sit here talking until the organizers kick me out.
I have a question. This is sort of an extension for the question that I asked to the first speaker of today. It's about the concept detector about atomic clock array, like the atomic clock array.
Okay, yes.
So this is also very similar. These are like millisecond clock separated by many light years and occurring naturally. My question is like, can we create something artificial and distributed possibly across the solar system, and it will be able to probe like different frequencies maybe, and also like different.
So I think I said something like this when I gave my talk here a few days ago. I said that I think in a couple of 100 years from now, detection of gravitational waves will be an undergraduate laboratory experiment. And I made an analogy that, for example, you can measure the speed of light now in an undergraduate lab. You just go take a 2-channel oscilloscope, and you plug in 2 cables to a signal generator, one cable which is a few meters longer than the other. And you can see the phase shift because it takes the signal longer to travel along one of those cables than along the other cable. So an experiment that a couple of 100 years ago to determine the speed of light was very complicated and challenging can now be done in an undergraduate laboratory in 5 minutes. And I think gravitational wave detection a couple of 100 years from now will be done just by using extremely precise clocks. You'll just place some very precise clocks around a room, and you can detect gravitational waves just by looking at correlation in those clocks. So of fluctuations in those clocks. So ultimately, you know, clock-based gravitational wave detectors, absolutely. I don't know the details though of this particular proposal. So I don't know if that's realistic or not. But the idea of using clocks as gravitational wave detectors, absolutely.
So I suggest
precise to a part in 10 to the 24 or something like that, and then you're good.
I suggest that we take the remaining questions to the coffee. So let's thank Bruce again for this very stimulating talk.